Equations one more time. We talked about three overriding questions to think about as you're solving trig equations. Take a look at whether or not the trig functions are the same. If the functions are the same, then you can factor. Are the angles the same, or are they multiples of each other? That's the question that we dealt with on the day 2 problem. So it was like, you know, if I have an angle that's 2x, I need to multiply my domain by 2, for instance. Today we're going to take just a closer look at the domain. So we're going to look at domains that are defined for radians, domains that are defined for degrees, and we did a little bit of that with the worksheet. And we're going to look at restricted domains, but we're going to also look at a domain for all real numbers. Okay, it's quite possible to solve these equations for all real numbers, in which case you have, you know, perhaps you have a sine graph that's, you know, continues like this. What we've been doing is perhaps looking at the domain or the solutions from 0 to 2 pi on that domain, and maybe we've been looking at, for instance, sine x equals a half. I want to know all the x values if I graph sine x versus x. I want to know what are the x values where the sine function is a half. And in this limited domain from 0 to 2 pi, there's really two locations, and that would be at pi over 6 and 5 pi over 6. And you solve that using reference triangles. But let's suppose I want to expand that and consider what are all the solutions for you know, an unrestricted domain, where the domain can be all real numbers. Then I know I have this solution, this solution, this solution, this solution, this solution, this solution, and so on, okay? Both extending to the right and to the left on that curve. So it's kind of a minor detail. It's not a really big deal. I think the more challenging part is actually solving the equations. So here were our day 1, day 2. I'm just going to scroll through this. And let's get to solving equations over the real numbers. So in the first example, we have 2 cosine x plus root 3 equals 0. The domain is for all real numbers. So if I was going to solve that, I'm going to isolate the variable. I'm going to isolate cosine x. That's equal to negative root 3 over 2. And then, just like what we've been doing, I'm going to draw a reference triangle. I take note of the fact that cosine is negative in the second and third quadrants. And I'm just going to draw reference triangles such that the adjacent side over the hypotenuse is negative root 3 over 2. So the adjacent side here is negative root 3. The hypotenuse is 2. I'm going to do the same thing in the third quadrant, negative root 3 and 2. And I should recognize from my experience with 30, 60, 90 triangles that this is a 30-degree reference angle, or we can call that pi over 6. So when I name my two solutions, I'm going to go from here, from 0, and I get x equals 5 pi over 6. And then when I name this angle here, again I have a reference angle of pi over 6, so it's pi plus another pi over 6, so that's going to be 7 pi over 6. So there's my two solutions, just considering all the angles from 0 to 2 pi. Now, in this case, my domain is all real numbers. So I want to think about the fact that I could actually have, you know, I could have this angle right here that terminates at this point. I called that angle 5 pi over 6. But I could just as easily start at the same initial side, rotate past it, terminate here, and now that's 5 pi over 6 plus 2 pi. And I could do 5 pi over 6 plus 4 pi, and 5 pi over 6 plus 6 pi. And I could write that out for the rest of my life and never finish. So instead, we come up with a formula. What would be a formula for 5 pi over 6 plus increments of 2 pi? Mark?
2n pi plus pi,
Wow, that was weird. Yes, let me get rid of that. Don't need to check for updates. Okay, so we have x equals 5 pi over 6 plus, you said 2n pi? Okay. Yeah, that seems to work nicely. And then the same thing for 7 pi over 6. So 7 pi over 6 plus 2n pi. And again, we're going to stipulate that n belongs to the set of integers because we want this to be 2 times 1 pi or 2 pi, 2 times 2 pi or 4 pi. So 2 pi, 4 pi, 6 pi. That's it. Okay, so just really, you know, we're solving the equation, same thing as you've done, nothing really radically different. We're just going to add 2n pi to the end so that we make sure that we include all of the possible rotations. So let's do another one. Let's take a look at 3 tangent squared x minus 1. Here I'm going to have tangent squared x equals 1/3. And then when I take the square root of both sides, I get tangent x equals plus or minus square root of 1/3. And that's the same thing as plus or minus 1 over root 3. And now I realize since I've got positive and negative tangent values, I have to draw triangles in every quadrant. And so to draw triangles where the opposite over adjacent ratio is 1 over root 3, my triangles are going to look something like this. Here's my root 3. And I should recognize the reference angle as being a 30-degree reference angle, or pi over 6 again. Okay, so this time I'm going to label my angles. X is equal to pi over 6, and I want to add the 2n pi because I need all the rotations. And then I have 5 pi over 6 plus 2n pi. And then I have 7 pi over 6 plus 2n pi and 11 pi over 6 plus 2n pi, where n belongs to the set of integers. Now, that's a lot of writing to do. So there's actually, in this kind of situation, there's a way we could think about this and write it a little bit shorter. For instance, if I take this angle, that's pi over 6. This angle is pi over 6 plus pi. Would you agree? And then this angle is pi over 6 plus 2 pi. You see where I'm going? Yeah, pi over 6 plus n pi. Because if I've already named pi over 6, then all I have to do is add pi to it infinitely many times. And that'll take care of both of these angles, both pi over 6 and 7 pi over 6. So as an alternate, I could write x equals pi over 6 plus n pi. And then the other angle I would have to do is 5 pi over 6 plus n pi, and that would take care of this angle and all the other rotations. So I would write 5 pi over 6 plus n pi, and of course where n belongs to the set of integers. So that would be my solution, and it's just a little shorter than writing what I wrote there in green. Your textbook will probably show it like this with the plus n pi, so when you look at the back of the book, you won't be thrown by that. And this is still, you know, what I wrote there in green, that's still a fine solution. There's no problem with that at all. But, so either one is fine. Questions about what I've done so far? All right, we have a few minutes. I think we can get to one more example at the end. So let's start it at any event. See how far we get. The other examples here in the middle they're pretty much what we've done. It's just the domain here is radians, the domain here is degrees, so I'm sure you can deal with that. But let's take a look at example 6. For this one, we have the domain is all real numbers, And this is a problem where I can't factor it. Yes?
I have a question for one. Just a quick one.
What?
When you divide, because you have two x or whatever it is,
Yeah?
you have x over 3, sum of x over 3, so
Yep.
1/3 x. Do you divide just by, like, say you got pi over 6, that's not what you get. Do you divide just by the 1/3?
Divide everything by 3.
Do you also divide when you get your answer, do you divide the n pi over 3?
You're going to divide the n pi by 1/3 as
So
well.
it would be 3 n pi.
Yeah, at the very end. Yep. Good question. Okay, so let's come back to this problem where we're looking at having to use the quadratic formula. Let me remind you, when you solve an equation like, you know, let's say it was 3x squared minus 4x minus 2 equals 0. When you use the quadratic formula, you're going to say x equals the, you know, negative b, which is the 4, plus or minus the square root of b squared, which is 16, minus 4 times a times c, all over 2 times a. Okay? And what you're setting equal to the quadratic formula is the variable. Okay? In a trig equation, the variable is the cosine. Okay? So in this case, it's the cosine of x, which equals the same thing that I put over there. It's negative b plus or minus the square root of b squared minus 4 times a times c, all over 2a. So when you do all that, when you simplify that a bit, you're going to get 4 plus and minus the square root of 40 divided by 6. When you take 4 and add it to root 40 and divide by 6, the result of that is something greater than 1. So there's going to be no solution for that part because the cosine of x can't be something greater than 1. When you take 4 and subtract the square root of 40 and divide by 6, then you get some decimal value. And I don't recall what it is offhand, and I'm running out of time. But the point is, you're going to have cosine x equals some constant, some decimal value a. In order to solve for that angle x, now you're going to have to do the arc cosine of a. Okay? I'm going to stop this recording now, but I'm going to finish this lesson. I'll add it to another recording, so you'll have both of those online tonight. So if you want to come back and look at the conclusion of this problem and then the solution of the others, that'll all be posted. Okay? So that's it for today.